For students in the back, can you hear me? Okay, great. Thank you. So remind me if anytime the microphone doesn't work. For those who didn't pick up the exam last time, is here. And also, I brought back some exam for the regrading during the weekend. I forgot to bring back. I will bring it back on Wednesday if you need those. And also, I posted an announcement yesterday that for problem 4, v equal to 0, and you didn't put the unit there. I think our TA is more strict than me. They put a -1 there, so it's perfectly fine. Bring your exam back to me. I will add that 1 point to you. And of course, if you find other grading mistake, you can talk to me after class. So you still have like 1 week to talk to me. So you do not need to spend the class time to check your exam. It's Friday, right? We have class on Wednesday, right? Today is Monday. Yeah, today's Monday. We will have class on Wednesday. Yes. Yeah. So let's continue. In the previous class, we talked about interpolation. We talked about how to have the U and V displacement X and Y if we know the nodal degree freedom. Basically, we derive shape function and interpolation function. And of course, based on definition of strain, for plane stress situation, we have 3 normal strain X, normal strain Y, and a shear strain. And we derived how to calculate the strain for plane stress situation. And this is the B matrix for Q4. And it does contain the variable X and Y, which makes more advanced element than the CST element. And we did one example. Basically, if we are given the nodal degree freedom, this one, and of course, nodal degree freedom I can give in this way, like this is the vector, this is the corresponding value. I can also say, okay, let's say node 3 move in the X direction for 0.1, move in Y direction in 0.2. You should know what it means. Some student complained to me after exam 2. I said, okay, the X node, node 2 move in the X direction for 0.1. They cannot make a connection. What does it mean? I think for senior engineer, for now, you guys should figure out if I say node 2 move in the X direction for 0.1, you should know that it means displacement in X direction equal to 0.1. So the nodal degree freedom can be given in any way. And the shape function specifically for this shape, we derive based on coordinates of 4 nodes. And so the interpolation function n1, u1, n2, u2, n3, u3, n4, u4. Same thing for the v. And for the strain, I just use the normal strain X direction as one example here. And of course, you can calculate, and you may practice in your homework or exam, that I can ask strain in the Y direction, I can ask shear strain, or I can ask you the strain components. Or I can go one step further, ask about the stress components. And converting from strain to stress is that the same as what we did in the CST element? Because no matter it's CST, or the Q4, the 4-node quadrilateral element they are considered plane stress situation. So for converting from strain to stress, it's the same, no matter what element type we use. And so this is the interpolation part, strain calculation part, and also stress calculation part. I didn't waste class time to calculate stress, but you should know what to do. So after interpolation, similar as what we did in a previous chapter, is that we need to figure out K. And K here is a little bit more complicated than the CST element because now the B matrix is not constant anymore. So we can not simply put the integration of A as time of A at constant because this is a function of xy, this is a function of xy. They do contain the variable xy here, right? So what we need to do is that it's truly the transpose B times C times transpose B. And then you have an 8 by 8 matrix, and for each component, you do the integration of A. And of course, don't be scared. I'm not gonna ask you really actually do this by hand calculation in the exam. So just use one simplified example here for you to practice. I gave this square element, K matrix for square element here. For this one, this is generally derived when it is a rectangular element, when it's 4 edge parallel coordinates, but it does not need to be square. the two edges does not use same length, but here is a special case. What if it's a square element? So I made homework, and the third problem is you need to use this one. And I provide this matrix in the homework problem statement. You can use it directly. And same thing for the exam. If I ask anything about square element, you need to use K, I will provide this one. And I also explained the last class that why if for square element, actually, no matter it's larger square or a smaller square, it does not really depend on edge length. And this is a simplified explanation that cancel out in the derivation part. So now we solve for the K part, and KQ equal to F. We want to use this equation to calculate Q. We need to figure out, okay, for different force, different type of force applied, how to put the force in the vector in the KQ to F. So this is very similar to the CST element. Is in the chapter 6, section 4.3, work equivalent nodal force. Again, we have three very similar situations. One is the concentrated force applied at each node. In that situation, you can just say no matter what direction it goes, you can decompose to x direction and y direction and put in the F vector. And also we can have the distributive force over the edge and also the body force. So let's do it one by one. First situation, if it's the concentrated force applied at nodes. So since it's the Q4 element, so we would expect that the F vector should be a vector with 8 components, right? F1 in the x direction, y direction, and node 2 x direction, y direction, 3 x direction, y direction, and 4 x direction, y direction. So if it's concentrated force, actually we can simply write as node 1 in x direction, 1 in y direction, 2x, 2y, 3x, 3y, 4x, 4y. If it's concentrated force applied at nodes. And of course, in the real situation, if there is a force, concentrated force applied at a certain point, you need to make that point at a node. Otherwise, there's no way you can put in the equation to calculate. The second situation is, of course, we talked about that in the CST element. The second situation is the distributive force over the edge. And this edge can be either 1, 2, 2, 3, 3, 4, right? 4, 1. But I just use edge 1, 2 as example. So let's say if the distributive force, let's say if this is a 4-node rectangular element, it's on this thin area. So there the thickness, that's edge length, is applied on this area. So let's assume that the edge length is this dimension. From this point to this point, this dimension is L, and the thickness is h. So the area, the force applied should be L times h. It's this area. L is h length and h is the thickness. And we can put the force in the x direction as Tx and the force in the y direction as Ty. And since it's a force applied on the area, the unit is Newton per meter square. So in this situation, for the force vector, how to write this force vector? If it's applied on edge 1, 2, and the edge length of edge 1, 2 is L, the thickness of the rectangular element is h, and x component tx, y component ty. How to write this vector, the 8 components in it. It should be very similar to CST element.
Yeah, and ty, is that the force or that the force per area? Is force per area?
Yes.
So will it be tx over 2 and then ty over 2 and then the outside the bracket is like L type thing?
Yes, and divide to node 1 and node 2. Yeah, and 3 and 4.
Oh, divide by 4. Then it'll be since these 4 nodes, the force will be distributed across the 4 nodes.
Wait, it's let's say this is node 1, this is node 2, node 3, node 4. It's only applied on edge 1, 2. There's nothing applied on edge 2, 3, 3, 4, or 4, 1. I'm asking you. So let me ask again, what are the 8 components? 8 components. 8 components in the vector.
Yeah. For F1x and F2x. So all the way up to x. Y over dy over 2, dy over 2 is the vector. Outside, we should spell something.
Yes, thank you. Actually, we can put the half outside of the vector. So let's do it this way. Thank you. So tx, ty, tx, ty, half, right? Yeah, thank you. So basically, of course, mathematically, you do need to do the integration. So it's again integration of shape function times the distributive force, and distributive force here is a constant force applied on this area in the x direction, y direction. And so for each component, you need to integrate shape function times distributive force, which is constant, over this area. You can check the textbook for the detailed derivation. But I talk about in the CST element, when you have a uniform distributive force over the edge, right? One in the x direction, one in the y direction, there's no reason that one node get a higher equivalent of force than the other because it's uniform distributed. So an easy way to understand it that, let's say, for the total force applied on the edge 1, 2 in the x direction is equal to area times tx force, right? Force per unit area, this is area. So, and then at node 1, 2, half. Same thing, the total force applied on edge 1, 2 in the y direction, area, force per unit area, and half to node 1 and 2. And for the node 3 and 4, there's really nothing, at least here, I just said it's only on the edge 1, 2. So the rest component should be 0. So this is what if we have a distributive force, uniform distributive force on edge 1, 2. Any question? Okay. The third situation, of course, is body force. The uniform distributive force over the volume. It could be body force or magnetic force. So it's very similar to the CST element. Let's say the body force I put as the x component at bx, y component at by. And since it's the uniform distributive force over the volume, the unit is Newton per meter cube. And we consider the area of our quadrilateral element is A, and the thickness, again, is h. So how to write this vector with 8 components? Anyone? How to write? Yes, thank you. Thank you. Oh, 4, yeah. And again, in the textbook, it has the integration shape function times the distributed force, which is a constant here of the volume, and integrate for the 8 terms, you get the equivalent of the force. But again, since it's uniform distribution of the volume, so what we can say that, well, they should get equal amount of the equivalent of the force. And the total amount of force applied in the x direction equal to bx Newton per meter cube times the volume, which is the force term. And equal divided to the 4 node, and similarly for the body force in the y direction. Right.
It's still going to be like, it is still going to be equal to a matrix times your Q vector, right? Whatever we're doing, even in this version still.
Yes, yes, FEA is about KQ equal to F.
Okay.
Yeah.
Well, I want to make sure that stuff got changed.
Yeah, this nothing changed. So for the whole FEA is always about K stiff matrix times Q node degree freedom equal to force applied. It's the same as bar element, 2D truss, bin element, CST, LST, or whatever element type you will use in FEA. It's always KQ equal to F. Yes. Any other question? So if no question, let's do an example problem. Actually, let's use the same example problem as CST element, but now we just use one single square element to model the structure. So material property, we have Young's modulus, Poisson ratio, 0.25. The thickness of the structure, 0.1 meter. This is same. And edge length of the square is 1 meter. Boundary condition is fixed at the bottom and the roller support at top surface. For the force applied, we have the uniform distributed force applied on top edge, 3, 4 in the x direction. Let's put as F here. So this is a distributed force. F equal to kilonewton per meter square. Apply on top edge. The question asks what is the strain, but of course I can also ask what is stress. Just go one more step. exact same as CST. So if you guys remember, we did this exact problem using two triangular elements, right? Structure is the same, dimension is the same, boundary condition is the same, material property is the same. Asking about stress, I just want to save some time here because converting strain to stress is the same. So this is the same problem that you need to use a square element to model it, not two CST element anymore. How to calculate the strain in this structure? How to calculate strain? Anyone? What is the first step? B matrix? B matrix, yes, strain equal to, let me write it down. Strain vector equal to B matrix times node degree freedom. B matrix we can derive based on the coordinates, because we already derived here. This is the B matrix for our rectangular element, for node rectangular element, but we don't know the Q here. So what is the first step? Yes, thank you. We do need, for this one, we do need to use K Q equal to F, right? Thank you. So now KQ equal to F. Since this is a square element 1 meter here, and we can use this 8 by 8 matrix directly, right? How many components do we need in this 8 by 8 matrix for our calculation? 2, 4, how many?
Side of the square fixed, or is it just the bottom side of the square?
Boundary condition is the same. Bottom is fixed. Top is relative support. This I just put as x or y coordinates. It's not fixed on this edge. I put it this way, just coordinate system. Yeah. What are the 4 components? What are the 4 components do we need?
The exit. Node, the exit, the third node. Yeah, the intersections.
Don't forget the coefficient. Is this clear? Okay. So in this 8 by 8 matrix, because our boundary condition, let me go back to boundary condition again, is same as what we talked about in the last class, in the previous class. The bottom is fixed, which means that the displacement x direction, y direction at node 1 and 2, both of them are fixed, right? Since this is a roller support on top edge, it means that the node 3 and node 4, it can only move in x direction, it cannot move in the y direction. I put this here because this is just the coordinate system. You know that if this is 1 meter, this is 1 meter, this should be 0, 0, this should be 1, 0. It's only coordinate system, but doesn't mean that this side is fixed to anything. No, the only boundary condition is fixed at the bottom, roller support on top. So now we know that based on this boundary condition, the only free degree for them is U3, U4, right? So what you need to know is that in this 8 by 8 components matrix, you don't need all the components. Do not try to write every components in your exam. You only need 4 components, which is corresponding to whatever related to U3, U4, U3, U4. So you only need these 4. Any question here? Okay, now let's put in the KQ equal to F. U3, U4, right? And we have a vector with 2 components. What are the 2 components? What are 2 components in the 4th vector? 100 times 1. Yes. But don't forget this is a kilonewton. So if you want to get Pascal, just yes. Be careful with the unit. So let's convert everything to meter and Newton. So in the end, you will get a unit as Pascal. This is Newton, and the area of the edge for the force applied is edge length equal to 1, thickness equal to 0.1. And since it's the uniform distributed force applied on the edge, we take half to node 3 and node 4. So solving this 2 by 2 matrix equation, we have U3 equal to U4 equal to 2.5. Sorry, I should say that everything here you convert to Newton and meter, and when you calculate displacement is meter, and when you calculate strain, there's no unit. When you calculate stress, it should be Pascal. Now for the strain calculation, let's use the B matrix we derived. One of A equal to 1. And also you need to plug in the corresponding coordinates. So let's do it this way. Three y 3, x1, y3, x1, y1. So 1, 1, 1 minus y. This is 0. Yeah. So basically, the coordinate at node 1 should be 0, 0. Node 2 should be 1, 0. Node 3 should be 1, 1. Node 4 should be 0, 1. You plug in, and you get this B matrix specifically for our element. And then you can calculate. Well, let's put the old degree freedom here also. U1, V1, U2, V2, U3, we have 2.5. V3, 0, U4, V4. So now you can calculate this one. Actually, it's not that complicated because there are so many zeros here. Let's say the first component, you have this one multiplied by this one. And you can see that this is y, this is negative y, and this is 2.5, 2.5. So it's 0 because it's y, negative y, and then, yeah. 0, 0, 2.5 into negative 5. You can check this one. The x and negative x cancel out, and in the end you get 1. So, yeah. So this is a strain, and strain converts stress. Check the action node for the CST element is exactly the same. Any question? Yeah, question.
So is it barrel?
What do you think? Yeah, what do you think? You can compare your action node. You can check your action node and tell me. Yeah, check your action node for the 2 CST elements.
The period constant. Here. Or they always cancel out like that.
Good question. For this one, yes, I said for our quadrilateral element is more advanced, and it does contain the variable x and y. For this situation, for this specific situation, because it's a pure shear, or yeah. So because if you understand from the mechanics materials, you fix the bottom part and you apply a shear force on top edge, there's only one constant shear stress, shear strain components in your structure. There's no normal strain in X, there's no normal strain in Y. No normal stress in X, no normal stress in Y. There's only one shear strain, shear stress components. So that's why this is a simplified situation, it cancels out. But if you have more complicated situation, I use the I show you guys this one. Bending using the where is it? Cannot find it. Here. If you use, let's say, the one I showed here is a test element. You can use 10. You can use 20. Right. I think in my tutorial video 5, I compare actually 4. So CST, LST, which is 6 nodes, 6-node triangular element. I also compared the Q4, 4-node rectangular element, and Q8, 8-node rectangular element, and compare results. Because for this one, if you apply a couple here, it will generate bending moment. And then based on your understanding from mechanics materials, the actual stress, it should change, let's say, on the cross section, maximum compressive, linear change, 0 on the neutral surface, linear increase, maximum tensor at the bottom surface, right? This is what the stress actual change in your structure. This is what it will show if it's a CS element using 10. This is what happens if we use CS element using 20. And in the tutorial video, you can check what if we use 5 Q4 element or Q8 element. How does the stress result show difference? How it converge? Yeah, you can check my tutorial video for those. For this situation, back to your question, yes, it just happened in this situation cancel out, but that's not always cancel out. If you use the bending, apply to the bending situation, it will not. Yeah. Let's continue with the discussion about like which one is. Why is the same? Yes. So because of course for simplified calculation example during the class, we don't really have a lot of time to do more complicated situation. More complicated situation goes to abacus. For this situation, as I explained, because it is a situation that is a simple shear, there's only one non-zero stress component or one non-zero strain component, which is a shear strain or shear stress. So no matter you use CS element, which is capable of representing constant stress, or use more advanced element, Q4, it can have the variable X and Y in the stress or strain. It will still be constant because the original condition, the original stress in the structure is constant, right? So it's the same. That's why I didn't really like go one more step to go to stress, because that part is just repetition. So we are done with the. Any question for this one? Okay. What is the X and Y?
Yeah. Oh.
They cancel out.
How they do.
Yeah, they cancel out. You can see this one times this one. Well, this four common doesn't matter because multiplied by 0. And you have Y, you have Y here. Right. They cancel out. It's only because the stress in this situation is constant. That's why it cancels out. But if you go to more complicated situation, it may not. You may have the X and Y in your strain result. You may have the X and Y in your stress results. When you go to more complicated, it means that our Q4 element has the capability to represent linear change in the X and Y. That's what it means. So basically, you plug in different points in the Q4 element, you will get different stress and strain result. So this is chapter 6. And when we do the derivation of this chapter, we talk about that it's only applied to the 4 quadrilateral element when 4 edge parallel to the coordinates. It does not apply to any other situation because our derivation is based on 4 edge parallel to coordinates. But we know that in the real life situation, it does not necessarily that each element always parallel to the coordinates. For example, this is your project 2. The 4x does not necessarily parallel to coordinates, and also you can see that some of the elements, they are not necessarily really rectangular elements, just 4 edge quadrilateral elements. The interior angle does not necessarily be to 90 degree. So in this situation, well, we still need to solve the problem. So what we need to do is the isoparametric mapping, which is in chapter 7. I'm trying to confirm. Wait a second. Yes, chapter 7. Isoparametric mapping. Chapter 7, section 3.1. The first several section you can just read textbook. I'm not going to do it in the class, but we start from the section 3.1. So for this mapping, actually, we didn't really use the word as a parametric mapping before, but I think we did something similar. Let's start from something we did before in the simple situation, 1D situation. Remember that for the bin element, they have a different length of the bin. Let's say that in the physical coordinate, in the x coordinate, we have L for different element, different L for different element, and let's say this is node 1 and node 2. And let's consider this is in the physical coordinate or physical element. And we also talk about this in the for interpolation for point on the edge of CST or Q4. And we said we need to convert to in the reference coordinate S coordinate, which should always start from 0 to 1. In this way, we can have a one set of shape function to solve all problems. And let's say, again, this is node 1, this is node 2, and it's always from 0 to 1. And this is the reference element. And remember, we talked about that for the interpolation of this 1D situation, we have shape function m1 times u1, shape function n2 times u2. And shape function n1 is always 1 and node 1, 0 and node 2. So it's simply as 1 minus s u1. N2 should be 1 and node 2 and 0 and node 1. So it's simply s u2. This is shape function n1. This is shape function n2. Right? We talked about this one before. And we can consider this is actually the simplest situation for mapping. This is 1D mapping. We simply set S equal to X over L. So no matter what the L of the edge length, it's always from 0 to 1. And this is the 1D mapping. And now since we are dealing with a plane stress situation, let's assume that in the 2D space, XY coordinates, we have general shape quadrilateral element. And for this quadrilateral element, the full edge does not necessarily parallel to the coordinates, and the interior angle does not necessarily to be 90 degrees. Which in all situation, you need to use this kind of element for irregular shape. Let's just use this one as a general situation, XY coordinates, and we have node 1, node 2, node 3, node 4. And whatever we derived in the previous chapter doesn't work. So what we do is that similar as the 1D mapping we did before, we have a similar concept is that we make this, no matter what shape it is for the quadrilateral element, we map into a reference coordinate with reference element. And we can solve everything in the reference element. So the easiest way, of course, is we set a ST coordinate. And of course, we make a square element, right? And now this element becomes a reference element. And remember that if we want to use the equation we derived in the chapter 6, we always need to make this one as node 1, node 2, node 3, and node 4. This node order they are node label they are fixed. So for the coordinates, put this one as -1, -1, node 2, 1, -1, node 3, 1, 1, node 4. So the left one is a physical element. And right one is the reference element. So the basic idea that this one is a standard square element. We already have the K matrix. We can have the shape function because the coordinates are given. We have everything derived for this one in chapter 6. So basically, for any random general type of the quadrilateral element, if we can find a relation between these two, we can solve everything the reference element first, and then mapping into the physical element, and we can get the displacement result, strain result, stress result, whatever result you need. Make sense or not? So this is the general idea. We can talk about in detail in the next class. Thank you for coming, and have a great day.